Every major leap forward in astronomy for the last 30 years came from space. Telescopes launched specifically to escape Earth's atmosphere and finally see clearly. So when a telescope sitting on a mountain in Chile, still breathing the same air as the rest of us, produced first images this detailed, astronomers didn't just take notice. Some of them stopped what they were doing entirely. This is the Vera C. Rubin Observatory, and what came out of its very first nights of operation is already forcing a rethink of how ground-based astronomy is supposed to work. Stick with me, because this one's genuinely surprising. And if you want more real science breakdowns, subscribe now. Let's start with the camera, because everything else about this telescope flows from it. Rubin carries the largest digital camera ever built for astronomy. It weighs close to 3 tons. It stretches roughly 3 meters long, and it captures light across ultraviolet, visible, and near-infrared wavelengths simultaneously. Inside sit 189 individual sensors, precisely calibrated so their combined output stitches into one seamless image rather than a patchwork of mismatched tiles. The camera captures 3.2 billion pixels in a single exposure. To put that in perspective, one image can cover an area of sky equal to 40 full moons side by side. Compare that to Hubble, which captures roughly 1% of the moon's surface per image. Hubble was built to zoom in tight, revealing incredible detail across a narrow slice of sky. Rubin does the opposite. Instead of a window, it captures the entire landscape surrounding that window, all at once. And it doesn't stop at one picture. Rubin is designed to scan the entire visible southern sky roughly every 3 nights, for the next 10 years straight. Every pass becomes another frame in a decade-long time-lapse of the universe. That's the plan on paper. Here's what actually happened when the cameras turned on for the first time. In June 2025, after roughly 10 hours of test observations, Rubin produced a mosaic that astronomers immediately nicknamed the Cosmic Treasure Chest. It was a 25 square degree portrait of the southern Virgo cluster, the nearest large galaxy cluster to our own Milky Way, built from 1,185 individual exposures stitched into one continuous image. Inside it, millions of stars and galaxies, spiral galaxies stretching across the frame, pairs of galaxies caught mid-merger, twisted together like smoke, faint filaments linking distant clusters, and buried in the background, a sea of faint reddish galaxies, each one a potential host to billions of planets. That single mosaic represented roughly 0.05% of what Rubin is expected to eventually capture. The full survey is projected to record around 20 billion galaxies. The treasure chest wasn't the discovery, it was the preview. The next release made an even stronger case for what this telescope could actually do. Rubin's team released a wide-field mosaic of the Lagoon Nebula, a star-forming region roughly 5,200 light-years away. Most images of the Lagoon Nebula that people have seen came from telescopes like Hubble, tightly zoomed on the glowing gas cloud itself. Rubin's version was completely different. The nebula, despite spanning about 55 light-years across, occupied only a small fraction of the total frame. Surrounding it, in the exact same exposure, sat open star clusters, a nearby glowing nebula, and a densely packed globular cluster millions of years older than the star-forming region beside it. Objects sitting at wildly different distances, belonging to entirely different chapters of stellar history, captured together in one continuous image. That's the practical result of Rubin's field of view. It doesn't just show you an object, it shows you the neighborhood that object sits inside. Beyond the pretty pictures, Rubin's early tests already started doing exactly what it was built for, finding things nobody else had found yet. In that same 10-hour observation window, Rubin identified 2,104 new asteroids, including 7 classified as near-Earth objects. For context, the entire combined network of the world's observatories typically finds around 20,000 asteroids in a full year. Rubin found over 2,000 in 10 hours of test observations. Scaled across its full 10-year survey, Rubin is expected to catalog millions of new asteroids, potentially becoming the single most important tool humanity has for spotting objects that could pose an impact risk, years before they'd ever come near Earth. And asteroid hunting is only one of 4 major goals built into the mission. Rubin will map how galaxies cluster and move across billions of light-years, searching for clues about dark matter and dark energy. It will monitor the sky for transient events, supernovae, gamma-ray bursts, sudden stellar flares, catching them in the moment they happen rather than days later. It will track ancient RR Lyrae stars, a class of pulsating stars used as reliable distance markers, to map the outer structure of the Milky Way in detail nobody has managed before. And it will generate roughly 500 petabytes of data by the time the 10-year survey wraps. To understand why the early images caught astronomers so off guard, it helps to understand the problem ground telescopes normally face. Earth's atmosphere blurs everything. Temperature shifts, humidity, dust, even faint layers of turbulence invisible to the naked eye distort light before it reaches a telescope's mirror. That's the entire reason Hubble and James Webb were launched into space in the first place, to escape the atmosphere entirely. Rubin doesn't have that option. It sits on the ground, but its location on Cerro Pachón, in one of the driest, darkest, most stable air columns on Earth, combined with its three-mirror design and fully automated scanning system, lets it sidestep much of the distortion that limits typical ground observatories. The result is images sharp enough to genuinely rival, and in some respects match, what space telescopes produce. None of this works without an entirely separate achievement happening behind the scenes: the data pipeline. Rubin is expected to generate around 20 terabytes of raw data every single night. To handle that, engineers built a dedicated 100 gigabit per second fiber connection, carrying data directly from Chile to a processing center in the United States. From there, an automated system has to calibrate every image, align overlapping exposures, correct distortion, identify anything that moved between frames, and fold everything into a constantly updating map of the sky before a single scientist even looks at the results. What Rubin is building isn't a photo archive. It's a living digital model of the sky that refreshes every 3 days. A supernova ignites. Rubin catches it in near real time. An interstellar object streaks through the outer solar system. Rubin flags it. A distant star begins pulsing irregularly. Rubin logs the pattern immediately. That refresh rate is arguably Rubin's biggest single advantage. Most transient cosmic events, brief flares, sudden brightenings, objects that appear and vanish within days, have historically been easy to miss, caught only if a telescope happened to be pointed at exactly the right patch of sky at exactly the right time. Rubin removes the luck from that equation. Astronomers have started describing it less like a telescope and more like a citywide security camera network pointed at the universe. The RR Lyrae detections point to another significant use for all this data. These old, pulsating stars brighten and dim in extremely predictable cycles, which makes them useful as distance markers. In its earliest test images alone, Rubin had already identified 46 of these stars. Across the full 10-year survey, that number is expected to climb toward 100,000. Mapping enough of them builds a skeleton of our own galaxy's outer structure, potentially revealing faint streams left behind by smaller galaxies absorbed by the Milky Way long ago, along with hidden dwarf galaxies simply too faint to have been noticed before. It's worth pausing on the camera one more time, because the engineering here is nearly as remarkable as anything it's photographed. Beyond its 189 sensors and 3.2 billion pixel resolution, the camera relies on a set of fused silica lenses to keep every part of each exposure sharp, including one lens that holds the record for the largest ever produced for astronomical use. A robotic filter swapping system lets the observatory switch between ultraviolet, visible, and infrared observations in seconds, letting it move quickly between very different kinds of science on the same night. The comparison to Hubble is worth returning to because it captures what makes Rubin different rather than simply bigger. Hubble is built for precision on a small scale, a tight, detailed portrait of one object, revealing structure nothing else can match at that zoom level. Rubin is built for scale itself. Instead of one object, it captures the relationships between thousands of them in the same frame, the full context a zoomed-in image simply cannot show. They aren't competing tools, they're complementary ones. Hubble is the microscope, Rubin is the aerial view. One of the more unexpected outcomes of Rubin's design is how directly it opens astronomy up to people who aren't professional astronomers. Because its mosaics are built from over 1,000 individual exposures stitched together, publicly available viewing tools let anyone scroll through them, zooming from a wide cosmic landscape all the way down into individual stars. With that much data generated every single night, professional teams alone can't realistically comb through all of it. Rubin's scale requires more eyes than any single institution can provide. That openness matters even more for interstellar objects, visitors passing briefly through our solar system from somewhere else entirely. Astronomers estimate that roughly one interstellar object drifts through our solar system every year, but until recently, almost none were ever detected. The two that were confirmed and studied were both found almost by accident, spotted only days or weeks before they became too faint to study further. Rubin's wide field of view, combined with its 3-day scanning cycle, means it's built to catch faint, fast-moving objects like these far earlier. Across its 10-year survey, researchers expect Rubin to detect dozens of interstellar visitors, each carrying physical material formed around a completely different star system. So what does all of this actually add up to? For most of the history of astronomy, our view of the universe came through narrow windows. One object at a time, one exposure at a time, isolated snapshots studied apart from whatever surrounded them. Rubin's first images already make clear that approach is ending. What it captured in its very first nights wasn't just impressive, it demonstrated that the sky isn't a static backdrop dotted with fixed points of light. It's an environment in constant motion. A single mosaic held millions of galaxies. A 10-hour test run turned up thousands of previously uncatalogued asteroids. One wide-field image of a single nebula revealed an entire surrounding neighborhood that had never been photographed together before. And this is still just the beginning. The full 10-year survey has barely started. Its scanning cadence is about to start systematically flagging supernovae and other transient events in real time. Its RR Lyrae detections will keep building out the skeleton of our galaxy's outskirts. Its public data tools will keep pulling ordinary people into a process that used to be locked behind institutional access. By the time this mission wraps up roughly a decade from now, what we understand about our place in the universe may look noticeably different from what we understand today, built not from a handful of famous, carefully chosen images, but from a continuous, ever-updating record of a sky that never actually stopped moving. But perhaps the biggest shift Rubin represents isn't just technological, it's philosophical. For centuries, astronomy has often been driven by a simple question: what should we point the telescope at tonight? Rubin flips that question on its head. Instead of choosing individual targets, it watches almost everything. That changes the kind of science astronomers can do. Unexpected discoveries become much more likely when you're no longer looking at one object in isolation. History suggests that's exactly where the biggest breakthroughs often come from. Nobody pointed a telescope at Uranus expecting to discover rings. Nobody expected pulsars when radio astronomers first noticed strange repeating signals. And nobody predicted that the accelerating expansion of the universe would emerge from observations originally intended to measure something else entirely. The universe has a habit of surprising us. Rubin was designed to maximize those surprises. Every 3 nights, it effectively asks the same question again: what changed? Most of the sky appears constant, but hidden within billions of stars and galaxies are tiny differences. A star brightens unexpectedly, an asteroid shifts position, a distant galaxy suddenly hosts a supernova, a previously invisible comet begins falling toward the inner solar system. Rubin is built to notice every one of those changes automatically. That constant comparison creates something astronomy has never truly had before: a living archive. Instead of isolated photographs separated by months or years, scientists receive a continuous record of how the universe evolves over time. That's incredibly powerful, because astronomy isn't only about where objects are, it's about how they change. Some changes happen over billions of years, others unfold in a matter of hours. Rubin can capture both. One of the mission's greatest strengths is speed. Within roughly a minute of detecting something unusual, automated alerts can be sent to observatories around the world. That means another telescope can immediately begin studying the event while it's still unfolding. In previous decades, many short-lived cosmic events simply disappeared before anyone knew they had happened. Rubin dramatically reduces that problem. It's essentially becoming an early warning system for the universe. And that affects far more than professional astronomers. Space agencies planning planetary defense missions will benefit from faster asteroid discoveries. Researchers studying exploding stars gain immediate access to fresh observations. Even gravitational wave observatories may use Rubin alerts to locate the visible counterparts of distant cosmic collisions. In other words, Rubin doesn't replace existing telescopes, it coordinates them. Think of it like the difference between a security camera and a detective. The security camera watches continuously. The detective investigates when something important appears. Rubin plays the role of the camera, Other observatories become the investigators. Together, they create an entirely new way of exploring the sky. There's another reason astronomers are so excited: data. Not just the amount, the accessibility. For decades, obtaining astronomical observations often required applying for valuable telescope time months in advance. Competition was fierce. Many excellent proposals were never approved simply because there weren't enough observing hours available. Rubin changes that equation. Instead of collecting data only for selected researchers, it creates an enormous public archive. Scientists across the world can ask completely different questions using exactly the same observations. That means discoveries may come from researchers who weren't even involved in operating the telescope itself. Even students may end up making important findings. History suggests they will. Several significant astronomical discoveries over the years have come from people looking carefully at publicly available data that others had already collected. Rubin increases those opportunities enormously. Artificial intelligence will likely play a major role as well. No team of humans can manually inspect billions of changing objects every few nights. Machine learning systems will help identify unusual behavior, but human curiosity will still matter. Algorithms recognize patterns. People recognize significance. Sometimes the most important discovery begins with someone noticing something that simply doesn't fit. Rubin gives humanity more opportunities than ever before to notice those moments. There's also something deeply symbolic about where this observatory sits. High in the Chilean Andes, far from major cities, far from bright lights, built in one of the darkest places on Earth. For thousands of years, humans have climbed mountains to better understand the sky. Today, the tools have changed dramatically. The curiosity hasn't. In many ways, Rubin continues one of humanity's oldest traditions: looking upward, asking questions, and accepting that the universe often answers with something completely unexpected. Perhaps that's why the first images created so much excitement, not because they were beautiful, although they certainly were, not because they were detailed, although they clearly are, but because they hinted at something much larger. They suggested we've entered a new era of astronomy, one where the night sky is no longer treated as a collection of isolated objects, but as a constantly changing ecosystem. Every night, every week, every year, something changes somewhere. And now, for the first time, we have a telescope designed specifically to notice. 10 years from now, Rubin's database will contain hundreds of petabytes of observations. Future astronomers may spend entire careers studying information that hasn't even been collected yet. Children entering school today could eventually make discoveries using images Rubin captures this year. That's the remarkable thing about observatories like this. They aren't built only for today's questions. They're built for tomorrow's, including questions nobody has thought to ask yet. If history is any guide, some of Rubin's greatest discoveries won't arrive because scientists successfully predicted them. They'll arrive because the telescope revealed something nobody expected to see. That's happened before. It's likely to happen again. And Rubin has only just opened its eyes. If you want to follow every discovery this telescope makes, subscribe and turn on notifications, because Rubin's data keeps growing every 3 nights, and the next release could genuinely reshape something we thought we already understood.